what I'm saying here, this is a carbon-13 NMR spectroscopy that we're going to look at today. Last time we looked at infrared, and this actually is an infrared machine where you put the sample on a disc on just under this, on this plate here, and the light shines through the infrared, and that's connected up to a computer. There's a detector underneath this shiny silver plate. We'll also look at some infrared later on today, but the main focus is going to be the carbon-13. Now, carbon-13 is, I hope you remember from your sort of basic chemistry, it involves isotopes. So here I've got different isotopes. Do you remember what the difference is, or what an isotope is? More neutrons, yep. So differing number of neutrons. Same number of protons, differing number of neutrons. So hydrogen, we've got 3 isotopes of hydrogen. I've just given 2 here. The protium version, where it's only got 1 proton and no neutrons, and the deuterium version, which has got 1 proton and 1 neutron. Carbon has also got 3 isotopes. I've only shown 2 again. Carbon-12, where most of carbon is what, 98.9, round about there. It's actually slightly less than that. Is carbon-12, so it's got 6 protons and 6 neutrons. And then you also have carbon-13, which has got 6 protons and 7 neutrons. Now, the reason why this is important is the way NMR spectroscopy works is that if there's an odd number of protons or an odd number of neutrons, then it can be affected by a magnetic field, because what happens, the protons and the neutrons spin together as a couple, and if they're not coupled, then it will be affected by a magnetic field. So hydrogen 1, or protium, is affected by the magnetic field. Deuterium is not, because every proton is coupled with a neutron, so they'll spin merrily together and there'll be no effect on the magnetic field. Carbon-12, same thing. 6 protons, 6 neutrons. Every proton is coupled, no effect on the magnetic field. But carbon-13 has got an effect because there's 1 neutron that's not coupled. And so carbon-13 is affected by a magnetic field. So what would happen, and this also happens in the hospital when they put you in for an MRI scan. It's just, most of your body, of course, is water or carbon compounds that have got hydrogens attached. So you're not in the machine for very long. It could be 20 minutes, and that's enough where they could get a spectrum out of you and work out what's wrong with you. And so hydrogen spectra are also used a lot in chemistry as well, but they're a little bit more complex. So at level 3, we only look at carbon-13. You may have done hydrogen or proton NMR, as it's called, at university. I'm not sure. Anyway, the carbon-13 is more simple. So what, as I say, it happens is if the protons and neutrons aren't coupled together properly, so they're odd-numbered, then it will be affected by a magnetic field. It'll line up with that magnetic field. And then when you put a weak radio wave through there, it will cause the nucleus to sort of flip, and by that flipping, it'll sort of instead of pointing north-south, it'll now point south-north. That exact energy it needs to flip is going to be registered as a signal. So that's pretty much how it works. It only uses much lower frequency than what we saw with infrared. This is now in the radio wave, so it's even a longer wavelength, less energetic. And as I say, different nuclei will resonate at different frequencies. So a carbon nucleus will be different to a hydrogen nucleus, for example. And also these electrons around the nucleus is going to affect how much the nucleus is going to feel from that magnetic field. So this different nuclei is not important because you're only going to be dealing with carbon-13. 13, so you can forget about the hydrogen. But the shielding of electrons around it is going to be important. Okay, so guidelines, but we'll go through these again. We have to think of carbon environments, because when you see an NMR spectra, it comes up with certain peaks, not those squiggles that we saw in IR, and the number of peaks tells you how many carbon environments there are. I'll talk about that more later. Then this is this important bit about the shielding. The more electrons around the nucleus, the less it's going to affect the magnetic field. So it's the more upfield the signal will be. If it's attached to a very electronegative element, it's going to be what we call de-shielded. So it's going to feel the effect of the magnetic field, and so it needs a stronger signal to make it flip. Sorry, a weaker signal to make it flip, because it's less shielded. And that effect of the electromagnetic element can be felt up to 3 atoms away, or 3 bonds away. So that's one thing you need to know when you're trying to assign peaks to carbon atoms in the molecule. Then the height of the peak, ignore. That's not important. Not in carbon-13 NMR. So this is what it looks like. Can you see these? What we have normally from 0 to 210 to 20 along the scale. It's in parts per million. And the reason why we use parts per million is every machine can have a different magnetic field. You can't get magnets to be exactly the same. So what they do is they convert it to a standard form. So we're converting from hertz to megahertz through some sort of complicated formula. And so hertz to megahertz, mega is million, and so that's where that parts per million comes from. But again, just like the centimeters to the -1 in infrared, you only have to just use it as a unit. You don't need to know the background behind it. Then also we talk about the chemical shift. So if it goes down, we call it down field. It means it needs a weaker signal because it's been less shielded by the magnetic field. And up field is when you get close to 0. 0 is always one particular compound that they use, trimethylsilane, and that's used as the marker when you're trying to make sure that every machine gives the same result. They have to use that trimethylsilane. Right, so that's the first thing, the chemical shift. Upfield, closer to 0, downfield, closer to 200. And then, as I said, there's a conversion factor just to explain that ppm. Now, remember when we divided the infrared, do you remember how we analyzed the infrared spectra? Where did we start? What did we look for? We looked at the alcohol, so we looked for that 3000 marker, didn't we? That's it. So we looked for the 3000 marker, and then we looked in 4 regions. The 3000 is slightly to the right of 3000, slightly to the left of 3000, far to the left of 3000, and then far to the right of 3000. So we looked at those 4 areas. We do exactly the same thing for NMR. We can divide it into 4 areas. So that looks like an enormous amount of information. But can you see these blue lines? Yes. You do not have to learn these things off by heart. If you look at your what I've got, I can't point to it unfortunately, but you'll see that view, that C13 NMR correlation table next to the chat box. You will be given that in the task as well as the teacher marked assignment. So it's just like infrared, it's just a matter of reading. I'm just doing a pictorial presentation here. But can you see the 4 different regions? We're looking at this upfield, sort of 200 and beyond. Then we're looking in this where it's between 150 and 200. It's actually 5 regions actually. And then 100 to 150. So basically all your C double bond O, your carbonyls, are in this area. And why I've divided this into two is that normally 200 and above is aldehydes and ketones, and all the other carbonyls are in this between 150 and 200. Then between the 100 and 150 is the alkenes, so the C double bond C. A double bond de-shields the carbon. It takes electron density and draws it all into the one place, so the nucleus is affected, and that's why it's so far downfield. Oxygen, being electronegative, de-shields it more, and that's why the carbonyls are further downfield than the C double bond C. Then the other half, you'll notice there's two more areas. This one over here, this is where your carbon is attached to an electronegative element from 50 and above, so it's normally oxygen with perhaps nitrogen flicking in here. You can see nitrogen just comes in here, but otherwise everything downfield of 50 is nitrogen and the halides, and then otherwise closer to zero, sort of 20 and less, are the alkyl groups. But we'll do lots of practice, so don't worry about that. And then, as I've said, the less electronegative the atom, the more shielded the carbon. So if you've just got the hydrogen attached, it's more upfield. If you've got oxygens, it's more downfield. Also notice, if I have a carbon attached to a hydrogen, it's more upfield. As I said, the alkyls are 20 and higher, or lower if you like. This is a very good way to see if you've got a terminal alkene or not. So if you've got a carbon double bond carbon with hydrogen attached, it's more upfield. It's around about 110, whereas a carbon attached to other carbons is more downfield. So they'll be, if it's one other carbon, it's sort of sitting in the middle here, and if it's attached to two other carbons, it's closer to 150. So that's a good way of trying to work out, do I have a terminal alkene or not? How substituted is my alkene? And then finally, I've said the double bonds de-shield the carbon atom, and so that's why the double bonds are down here and the single bonds are more upfield. Okay, so does that give you a sort of pictorial presentation? So think of carbonyls all the way to the left, ketones, alkenes middle left, electronegative middle right, and alkyl far right. That sort of gives you an idea of where things are. Now what can we find out? So it's a minimum number of carbon atoms in a molecule, and I'll talk about that. That's a carbon environments again. I'll talk about that just now. Then also the functional groups. Now does this look very similar to what we saw with the infrared for points 2 and 3? Does it look similar or not? Okay, not sure. Okay, so the remember with the infrared, you could find out if you had a alkene, a carbonyl, an alcohol, and so on. So you can get similar functional groups. Aldehydes and ketones are great in the NMR spectra. You can also work out if you've got other carbonyls, and it also shows the alkenes, and it tells you also a bit more detail about the alkenes that the infrared didn't do. And then it also tells you about the electronegative elements attached to carbon because they get shifted downfield a bit. What you can see is where the carbon and oxygen is present, the halogens and the nitrogens are not so easy to decide. There you're going to need the mass spec as well as the infrared with that. Okay, and as I said, when you're doing the task, the functional groups you see in the IR should also appear here in the NMR. And if they don't, if there's a contradiction, it means you've misinterpreted something, or you've, just always double check, because perhaps there's an anomaly. Something like an aldehyde is often a little extra squiggle, so you may have to, it may just be a nonsense peak. So make sure you match them all up. And then, as I say, the elements you can check by comparing what functional group is present, and as you can see, the oxygen comes up clearly, but not the nitrogens and the halogens. So, what do we mean by carbon environments? If a carbon is in exactly the same environment, so is it bonded to exactly the same other groups or atoms, then it's an identical environment. It'll feel the same effect of the magnetic shield, so it's going to need the same frequency to flip the nuclei. So in the first one, can you see the first carbon has got 3 hydrogen atoms attached and 1 methyl. The second carbon has got 3 hydrogens attached and 1 methyl. Are they in the same environment? Yes or no? Yes. So I've only got 1 carbon environment. So I've shown them both as blue. So I'm only going to get a single peak for ethane. What about propane? If you look at the ends, can you see each carbon on the end is, yep, correct, you won't just get 1 peak because the end carbons are the same, 3 hydrogens and an ethyl group. And this one's the same, 3 hydrogens and an ethyl group. But the middle carbon is different because it's got 2 hydrogens and 2 methyl groups attached. So I'm going to get 2 peaks in that NMR spectra. And then how many do you want to guess for the next one, butane? Still 2, correct, well done. So the ones on the outermost have got 3 hydrogens attached and a propyl group for the blues. And the red ones have got 2 hydrogen atoms, 1 methyl group, and 1 ethyl group attached. So they're exactly the same, 2 hydrogens, 1 methyl, 1 ethyl, so exactly the same environment, same amount of deshielding, so they'll resonate at the same frequency. And what about the last one? How many carbon environments? 3, correct. Again, the ends, the 2 blue end ones, 3 methyls, 3 hydrogens and a butyl group. The 2 red ones are a methyl, 2 hydrogens and a propyl, and the green one has got 2 hydrogens and 2 ethyls. So it's different to any of the others. So pentane will have 3 peaks, and we will see pentane soon. Okay, so let's have a quick quiz. Now here, just look very carefully. I have put OH in, so these aren't just hydrogens. So think of what the carbon is attached to. This one is 3 hydrogens and a hydroxymethyl. This one has got an OH, 2 hydrogens and a methyl. Will it be the same? So it's got 2 peaks, correct. What do you think about this one over here for B? Do you want to have a go? 2, correct. Because the 2 end ones, if you sort of just look for the symmetry of the molecule, that often helps. So it is a fairly symmetrical molecule. So that still has 2. What about the number C? 3, correct. Because this carbon is not the same as the blue one, because this one's got 3 hydrogens and a hydroxyethyl, whereas the green one has got a hydroxy group, an OH, 2 hydrogens and an ethyl. And number D. It's actually got 4, this one, because every one has got slightly different groups on it. If I look at the middle ones, I think the end ones are quite clear, well, if you spotted that OH. But the middle one, this carbon has got 2 hydrogens, an ethyl, and a hydroxymethyl, whereas the red one has got a methyl, 2 hydrogens, sorry, I've just done the red one. The red one's got a methyl, 2 hydrogens, and a hydroxyethyl. The green one has got 2 hydrogens, an ethyl, and a hydroxymethyl. I might have got myself a bit muddled, but can you see that the groups are different? So if they've got different groups on, then it'll be in a different environment. And E, I know we're going quite quickly through this, so you most probably aren't having a good look at it. Three, it's again going to be 4, because let me just do the colors. This carbon over here has got 3 hydrogens, and although it's got a hydroxy propyl, the OH is closest to the carbon, so it's going to be deshielded more than this carbon over here, blue carbon, because that's got the 3 hydrogens plus the hydroxy propyl. But can you see the OH is now further away from it, so it's not going to be deshielded as much. So that peak is going to be slightly higher up than the blue peak will be slightly more upfield than the purple peak. So they'll be close together, but they'll be in a different environment. And number F, I hope you can see, is totally symmetrical, so it'll be 3 peaks. Okay, the green one, but these red ones have got exactly the same groups on it, and the blue has got exactly the same groups on it. Then G, I don't want to trick you, so I'll do this one first. It's got 3 groups. Sometimes it's difficult for students to see because you tend to see it as 2D and you don't see it as 3D. So you think, this methyl group is closer to the OH, so it'll be more affected. But actually in 3D, if you saw this molecule in 3D, they're in exactly the same position. So both carbons here are the same distance away from that OH. And they both attach to 3 hydrogens and a hydroxyethyl group where the OH is furthest away from them. So can you see that those 2 blues are actually identical? Yep, okay. And then what I've got here, though, in H, it's not symmetrical. So because I've got an ethyl here and a methyl, so it's not symmetrical like 2 methyl groups here. So I've got 5 carbon environments here. And if you look at the recording, you can pause the video and just count what groups are attached to each one. And finally, for the last one, would you like to have a go at how many carbon environments there are? 3. Correct. Well done. Okay, so let's have a look now, and we're going to do that same sort of 4 areas to see what we've got. Now, I've told you this is an aldehyde or ketone, and you can see it's an aldehyde or ketone because the peak is 200 or above. They can start from like 198, but basically if they're above 200, you know it's an aldehyde or ketone. Ketones tend to be higher up, closer to 220, but you will see later in an example, I think in next lesson, where you see a ketone actually in the similar position to this. So look above 200 or 200 and higher. If there's a peak there, you've got an aldehyde or ketone. If you've got now the next area you look is from 200 to 150. There's nothing there. Okay, so there's no ester, acid, amide, or acyl chloride, because that's where they all fit in. Then you look in the 150 to 100, and if there's no peak there, you know there's no alkene. And then you look in the 100 to 50, this area over here, you can see this one has just come in. Now, remember I said that's your, looks like an OH, okay? But what will also fit in there, and if you look next to the chat box and you look at the 1, 2, 3, 4, the 4th one down, if you've, or 4th and 5th, if you've got fourth and sixth. If you've got a carbon next to a carbonyl group, that also tends to be de-shielded. Because remember I said de-shielding can affect up to 3 bonds away. So we know we've got a carbonyl because of this carbonyl peak down here. So that means we've got to have a carbon next to a carbonyl. And that's why it'll be this one at around about 52 or so parts per million. And then the final thing is we look further down below 50, and you should always get some sort of alkyl peak there. And the methyl tends to be the lowest one down. In this particular case, they're slightly above 200, above 20, because they've been de-shielded by the carbonyl. Right, and those are the alkyl groups. How many carbon environments? I see you typing there, so you might have a question. 4 carbon environments, great. Okay, and that's what it actually is. I wouldn't expect you to come up with that structure based just on that NMR, because you need the information from others as well. So don't be horrified and think, oh, how did you get that? But if you look at that structure, I hope you can see there are 4 carbon environments. The carbonyl, the carbon next to the carbonyl, so that's peak number 2. We're always starting from the most downfield going up. So that's peak number 1, peak number 2. Peak number 3 is this one here, and peak number 4 are the 2 methyl groups. And you can see that they're fairly close together. Okay, here's another one. So I've reproduced this so we can, I'll be highlighting things along. Look at the most downfield, and there's no aldehydes or ketones. Then you look between 200 and 150. That's where your other carbonyls are, and they're all sort of in that type of area. You can differentiate a bit, but sometimes if there are other groups around, they can overlap a bit more. We can see there are no alkenes. There's no peaks between 150 and 100. We can see there's a peak over here at 60. Now, we do have a carbonyl peak. So remember what I said last time? If we've got a carbonyl peak, it could be the carbon next to the carbonyl peak. But if you have a look, it's not, this peak at 60 is a bit too downfield. Look for the carbon next to a carbonyl, carbon next to a carbonyl. They're not quite at 60, whereas where we've got a carbon next to an oxygen, they most probably, it's in the right area. This is sort of, oxygens can be anything from 40 to 80, they can, but sort of in that area. So we've got a carbon next to an oxygen. That is most probably the carbonyl one, because you can see that's within more or less that range. And then, of course, the last are the alkyl groups. And how many carbon environments have we got? Ooh, 8. I'm not quite sure where we got 8 from. There's a peak here. Remember, the carbon environments correspond to the peaks. So I've got a peak 1, 2 at 60, 3 at round about 35, 4 at 20, and 5 at round about 15. So I've got 5 peaks. So I've got 5 carbon environments. Oh, I see. You were looking at these little ones over there. And no. These are what we call decoupled peaks, and sometimes you see something like this, because one way when you do NMR in more detail is the computer can work out the area under the peak. They use calculus, and that will correspond to the number of atoms actually present. Remember, I said the height of the peak doesn't matter. It's the area under it that does matter. And so it's sort of just thickening out a bit. They've decoupled it to remove that area bit. But yeah, okay, I can see what you mean. If you see things like this, don't worry about it. That's not an extra peak. Okay, you sometimes get that in these NMR peaks. Okay, I didn't even see that, so that's good. And this is what it is. Can you see these at ester? So carbon 1, the peak 1 is the carbonyl. Then peak number 2 is the carbon next to the oxygen. And then notice we've got peaks 3, 4, and 5. Can you see, well, the methyl groups are quite close together. So the methyl group over here and the methyl groups in number 4 are quite close together. They're 20 or less. And as I say, the more substituted, so the less hydrogen it's got around it, and the more substituted, more carbons, the more de-shielded it is. Because carbons are quite big molecules compared to hydrogen, so the electrons are further away in the bond, so the nucleus gets affected by the magnetic field more. Whereas if in hydrogen's a small atom, can get close to the carbon, so its electrons are much closer to the nucleus, and so it's more shielded, so they tend to be upfield. Okay, I'm going to go a little bit faster now because I just see the time is going. What we've got here is, again, look in the aldehyde area, there's nothing there. Look between 200 and 150, there is something there. No alkenes between 150 and 100. There's nothing in the alcohol range. But because we've got a carbonyl, we know we've got to have a carbon next to a carbonyl. And so that's what this outermost peak is, and then we've got the alkyls. You'll be differentiating the alkyls in a bit more detail when you're using all three spectra together. And I hope you can see there are 1, 2, 3, 4, 5 carbon environments. I see now that's all double peak. It's partly because they've tried to reduce that area. They've tried to make them more peak-like. And can you see these? Number 1 is the carbonyl, and number 2, this is actually an amide. So this is the 2 next to the carbonyl. Right. An alkene. You can spot an alkene very easily because it's got peaks between the 100 and the 150 range. So starting in the unusual systematic way, no aldehyde or ketone, no carbonyls. Then we do have an alkene. And notice we know exactly what type of alkene it is. One carbon of the double bond is attached to 2 hydrogens because that is sort of below 120. Can you see that? 110 to 120. This is on around about 110, in fact it's around about 109. So we know that's attached to 2 hydrogens, it's more shielded, so it's gone up. This one is more de-shielded, that's right, this is a terminal alkene. This one is got 2 alkyl groups attached because it's over 140. The ones that have got a hydrogen attached as well as an alkyl group tend to be in this middle range over here. So it tells you a lot about the alkene, what it looks like. And then you've got no electronegative atoms, and then you've got the alkyls. And, pointing out, the carbon next to the alkene is de-shielded, so these R groups here attached to that carbon will be these 2 over here. Can you see then the 10 to 40 range? They've moved up a bit. And then your methyl groups are sort of 20 and below. So you've got 5 carbon environments, and can you see that's your terminal alkene is peak number 2, whereas a substituted one is peak number 1. Okay. This one very quickly, this is now an alcohol, and you can see I've got no carbonyls, no alkenes, and I've got an electronegative element there that's quite high up. Oxygen tends to be quite high up there. And then these are all the alkyl groups. And you'll see as I move further away from the oxygen, it gets affected less. So that's how they correspond. Carbon 5 is the furthest away from the OH group. And let's now practice. We've got a few of these. Let's see, what do you think this top one represents? So go through, do I have aldehydes, ketones, do I have carbonyls, do I have alkenes, do I have electronegative, do I have alkyl? It's an alkene. And if you look at where it is, it's between 120 and 140. So do you think it's a terminal alkene? Do you think both carbons have got a CHR attached? In other words, is it this terminal alkene? Is it a CHR or is it a CR2? It's a CHR. And compared to down over here, that's definitely a terminal alkene because it's below 120. This could go either or. It's most probably a CHR because a CR2 tends to be a bit higher. So going through the various things, those are the various areas, and you can see both of these are CHR. I can just see you typing there. Okay, yep. So, and then if I go through these very quickly, those 4 areas, can you see there's a terminal alkene, number 2, whereas the lowest peak, the most downfield, is a CHR peak. They haven't shown the H, but of course you know the carbon has got 4 bonds, so as only 3 are showing here, you know that the 4th bond is to a hydrogen. Okay, here's another one. So you go through it and you can say, right, no aldehydes, ketones, no carbonyls, no alkenes, no electronegative elements. Here, this could be just all alkyls, but it's quite downfield for straightforward like pentane or something. You know, that variation. So I've most probably got a nitrogen or something in there, or something. And in this case, I do have, this is an amine. The nitrogen of the amine has shifted number 1 and 2 sort of more downfield than a normal alkyl group. Whereas here, I've got, if I go through those areas, I've definitely got something that's very electronegative, and it's most probably an oxygen. So if you have a look, that's carbon 1 attached directly to an OH group. And I've got the 3 carbon environments with the 2 methyls in the same environment. Okay, so what I want to do for the remainder of the time, I've got 11 of these, but I don't think we're going to get through all of them. So towards the end, I might just flip through, and if you're looking at the recording, you can pause it. What we want to do now is match what we see in the IR with the, well done, with the what we see in the NMR. Because for merit, you need to collate 2 spectra together. For achieved, you just have to find something in each spectra, but they don't have to be related. For merit, you've got to tie 2 together. So for instance, you've said it's an aldehyde, quite correct, but you've got to say what makes it an aldehyde in the IR and what makes it an aldehyde in the NMR. So I use always my IR as my basis. Remember the 3000 just to the left, just to the right, just to the left, and so on and so forth. Because you should also say what is absent as well. Don't just say what's present, say what's absent. So why, you said it's an aldehyde, why isn't it an ester? Why isn't it a carboxylic acid? That's also important. Okay, and it's a W in the aldehyde. So first of all, starting alkyl group, look for the 3000 just to the right, alkyl. You can match the alkyl in the NMR. Just to the left of the 3000, alkene, missing in the NMR as well. And there's, remember the alkene peak is also over here. So I've just put it together so we can see all the places for the alkene. So we know it's not an alkene, and you would have, if you wrote it on the spectra like this, you don't have to give as full a discussion, and you'd have to write less because you're giving the information here. So a really big tip is write on your spectra. Then you don't have to go, there are no peaks in the NMR, C13 NMR between 100 and 150, which means there's no alkene. You can say all those words by just simply saying no alkene and drawing a line between the 100 and 150. So that's enough. Okay. And then you look, as I say, you look further upfield, or further, you know, the 3000. There's no OH or that may be an NH. Okay, we don't know. So it could be that. And we definitely have, okay, we're first doing this area. But we know there's no OH, so we know that this thing at around about 52 is not from an OH, because we're not seeing anything here. Now we go to the far right. There is the carbonyl. There's my carbonyl. They match up. And if you look at the area, it's in the right place for an aldehyde. So mention that, right place for an aldehyde, and that is in the right place for an aldehyde. And then say we know it's an aldehyde, not a ketone, because we've got that very clear W over there. Now you would then go in and explain a bit more what this one is from. Okay, we need the mass spec for all the final thing, but this is, what do you think this peak is from? If we've got an aldehyde, remember, if we've got any carbonyl, the carbon next to the carbonyl is going to be shifted downfield. So you can say this is the C next to the CO. Where would it appear? So round about over here. Okay. Right, and then I've given here a bit more extra detail. It can't be an ester because it's a it's incorrect position. All right, that's right. You've got to give a bit of detail why it's not. And remember, there's no position over here. There's no peaks over here for an ester carboxylic acid acyl chloride. So we know this is not an ester. And so it's more evidence that it's not this, so it's more likely to be the aldehyde. And so there is our carbon next to the carbonyl. And it can't be an NH because well, that could be an NH. Perhaps we need the mass spec to rule that out completely. Okay, so this is the way you'd link it, and that is the molecule if you wanted to know. It is a spectrum we've seen before. Let's now do the next one. So if you look through the various things, okay, we've got the alkyl, okay. These are alkyls, but they've been affected by something. So it's not a straightforward alkyl. Remember, you always got to have a methyl, and it's the most upfield one. Then we look just towards the left, and there's no alkene that matches. There's no thin, narrow peak there. Then we look more to the left. There's no OH, okay? And we know there's no OH from a COOH because there's no triangular thing over there. But we do have a carbonyl peak over here, and we do have a carbonyl peak over there. Now, remember what I said, the more downfield, it's got to be an aldehyde or ketone. So this is more likely to be the ketone because we can't see a W there. And then I put a bit of red in there to say what it can't be. So you can choose, and you could have said it's not a carboxylic acid. I said there's no triangular peak. So write those details on. And there we've got two downfield. So this is, can you see the ketone? If a ketone is there, it means I've got to have two carbons adjacent to a carbonyl. So I must see two of those peaks being shifted downfield. Okay, number 3. So again, we can see straight away it's a carbonyl, but let's go through it systematically. There's my alkyl peaks. Okay, we know the top one must always be a methyl, so we can always assign that to a methyl. No alkenes. Everything correlates. Okay. Look further to the right. Left, sorry. There's no triangular COOH peak, no parabola for the OH. So we know it's not a carboxylic acid. But if we look over here, we know it's not an aldehyde or ketone because there's no peak further downfield. So it must be the ones that fit round about between the 150 to 200. Of those 4, we know it's not a carboxylic acid. Yep, great, you can see that. So we know it's not aldehyde or ketone because that's missing. We know it's not a carboxylic acid, or we can cross out the carboxylic acid because there's no triangular peak. We can also cross out the amide and the acyl chloride because of where this peak is. Remember, the amide comes below 1700 and the acyl chloride goes closer to the 1800. So that's why we can cross those out there, reference it to the infrared. And yes, we are left with an ester. So we've got these two peaks. Remember, will be the CO peak next to the ester, if I just show it. So number 2 is the one attached to the O, and number 3 is the one next to the carbonyl. And then we've got 1, 2, 3 methyl groups. So this peak over here is the methyl group, and number 4, those ones over there. Okay, right, what's this one? Hopefully you can see straight away. Carboxylic acid, and you can see it straight away because of the triangular peak. So, but do systematically look for the 3000, a little bit to the right. There's some alkyl groups. We've definitely got carbons and hydrogens. We can't really see whether there's an alkene or not, but we do expect to see one peeping out just below 1600 if there was an alkene, and there's nothing, and we know there's nothing. We can confirm there's nothing because there's nothing in the NMR. So you can say the IR, we can't see if it's an alkene clearly, but we know from the NMR that it's definitely not an alkene. Okay. Now, as you can see, you're typing, but keep on typing and I'll carry on. Then we look more to the left and we can see the triangular peak. Right. Okay, so are you on your way off now? No. Okay, yeah. Okay, great. So now we look over here. We know there's no aldehydes or ketones. This is a carbonyl, but from the IR, we can cross off quite a few things here. We know it's not an ester because there's nothing in this area that gives an CO peak. We know it's not an amide because the infrared carbonyl is too high. And we know it's not an acyl chloride because the infrared carbonyl is too low for the acyl chloride. So we just left with the carboxylic acid, and we know it's that anyway from there. And there you go. Okay, 4 peaks. So you because you've only got 4 carbon environments, even though you've got 5 carbons. Now, if you have a look at this, what would your first guess be? Based sort of on the IR, and then you confirm it with the NMR. So going through the process, there's an alkyl. Remember, the one that's most down upfield is always the methyl. Can you see this one's been shifted quite a bit? It's not below 220, so we know there's an electronegative element here affecting things. There's no alkene. We don't see anything. You might be tempted to think this is part of an alkene. Okay, that's an easy error to make, and you could say, it's a twin peak. One of them might be an alkene. There's no problem with that. But then you can say, we know it's not an alkene because there's no peaks here in the NMR region between 100 and 150. And yes, it's a nitrogen atom affecting things, and we know it's the nitrogen atom. You'll see in the mass spec why as well, but the NMR also, IR clearly tells you as well. Remember, this twin peak is a primary amine. And we know there's a carbonyl, it's an amide we've got here because of this. We know it's an amide because it's below 1700 as well, so mention that. Okay, we know that's not from an aldehyde or ketone because there's nothing over here. Right, so we can cross off all the others because there's no CO, so it can't be an ester. It can't be an acyl chloride because it's not high enough. And it's not a carboxylic acid because we don't have that triangle. And there we have it. It's an amide. And although it's got 5 carbons in it, it's only got 3 peaks because these 3 are in identical environments. Okay, number 6. So we're sort of halfway through these. We've got about 5 minutes left. Hopefully you can see, well, let's go through the whole thing. Alkyl, okay. Now can you see I have got an alkene, and can you see this terminal alkene? If you have a terminal alkene, you should see a peak there. If you've had just a totally substituted one like CR2, you'll see a peak on this side, but you won't see a peak over here because there's no hydrogen attached to a carbon of a double bond. But if you have a terminal alkene, you should definitely see a peak over there. A CHR would also give that peak. And so we know it's an alkene. We know we've got an OH from there, and that's confirmed by this peak here at 70 something. And we know it's not an aldehyde, ketone, carbonyl of any sort because that's missing. And this R group has just been shifted down because it must be close to the O or the alkene. So if we look at it, can you see the carbon number 1 is the one that's the most substituted double bond. Carbon number 2 is the terminal alkene. Then we get a carbon with an OH that's been affected by both the alkene and the oxygen, and that's why it's further downfield. It's not sitting at 60 anymore, it's gone down. Number 4 has been affected by the OH as well, because remember, up to 3 bonds away it can find it. But number 5 is far enough from the oxygen, it doesn't really feel it, so it's sort of sitting where methyl is, of around about 10. Okay, because I'm now not having much time at all, I'm just going to go very quickly through it while I'm clicking. See if you can work out what it is, and can you see it's a secondary amine. We can see it from there, and we know there's no carbonyls, and if it's secondary I must have 2 peaks shifted downfield because that nitrogen must be attached to 2 carbons, and both of them have been affected. Then here's another one, and I hope you can see this is a primary amine as we had before. Well, we had that primary peak before. We didn't have a primary amine before. This you can dither about. What is this? Is this a funny carbonyl? Is this a double bond, carbon-carbon double bond? This is where you use the NMR to work out what that is. We know it's not an alkene. We know it's not a carbonyl because there's nothing here. So that must be that NH-WAG or BENZ that you can get. Okay, and there is our compound. Now, as I say, I do not expect you to get this exact compound just from these 2 spectra, so in case you're worried about that. Here's a number 9, and I hope you can see it's an alkene. First the alkyls, look for the carbonyl, the C double bond C or C double bond CH. We don't have an OH or NH. This could be a possible CN, but because nothing's showing here, we know that is not a CN. So this must be the peak from a carbon next to the double bond. So carrying on about the carbonyls. Oh, in this particular case, actually, and you wouldn't see it without the mass spec, but we actually have a halogen here. So there's actually a halogen in this particular one, which you wouldn't have known very much. From the IR, you can see all these peaks here, so you can suspect it. But as I say, the IR fingerprint you use only to confirm. You don't use it to base an assumption on. But so you'd get it from the mass spec, and you'd confirm it, that there are CX peaks here. And this is number 10, and I hope you can see that'll be an alkene, and we can see it's an alkene over here, and what is not, and there it is, and this one also has the halide in it. And the last one is, if you have a look, it's not an alkene, it's not an aldehyde or ketone, and what we have here, if you look over there, CX, and this is actually an acyl chloride. It's confirmed it's close to the 1800 over there. Right, and I think that's it. Yep, it is. So I'll go back here. Does this help in how to get the 2 together? Right, so next week what I'll do is I'll do the basics of the mass spec, and then we'll look at also all three together. And if there's not enough time to do all that, I might just do an extra lesson, just record it sort of sometime on the Friday. So at least you've got it if you want to work over the holidays and just do this. Because I think if you know this, you could actually go straight away to the 3021 and just simply do the assessment task, the assignment, and send it in, and then I could send you the assessment task as well. Okay. Right. Well, all the best. Enjoy this